So the answer to the question of did duckbills walk on their back legs or did duckbills walk on their front legs on all fours, the answer to that question is yes.
Welcome to Science for the People. I'm your host, Marian Kilgore. Joining me is Dr. Scott Persons, a paleontologist and researcher at the University of Alberta. He's a children's book author and the co-writer and presenter of the University of Alberta's widely successful paleontology online courses. Dr. Persons is also a science columnist for CBC Edmonton Radio and TV, and has been featured on National Geographic and Discovery channels and in Smithsonian and Discover magazines. He has over 60 formal scientific journal publications and has taken part in fossil hunting expeditions throughout the Badlands of the American West, as well as Mongolia, Tanzania, and Argentina.
We know from fossil trackways that hadrosaurs, the duckbill dinosaurs, are capable of walking on all fours with their forelimbs, just adding a little bit of extra support. But it's also clear based on how much longer their back legs are compared to their front and how much thicker they are, that these were animals that were definitely capable of rearing up and standing just on two legs when they wanted to. And the thinking has been that probably when they went to run, when they were moving at their maximum speed, they essentially popped a wheelie. The short little front legs said, okay, big legs, you guys take over. And they probably relied just on their back legs. We call that facultative bipedal running.
Your public outreach work is pretty broad-ranging, but I'd actually like to start with some of your research into dinosaur tails and bipedalism. So why is understanding tails important to understanding how dinosaurs moved and interacted?
I should point out that in most cases, a tail is just a big part of a dinosaur. Just physically, it makes up a big chunk of their anatomy. On, say, Tyrannosaurus rex, well, more than half of that animal's body length is tail. So it's this big thing. It represents a very large investment on the part of the dinosaur. And if you read most children's books, if they mention the function of the tail of T-Rex at all, the usual explanation that you get is what I call the seesaw hypothesis. That's the idea that Tyrannosaurus rex, because it stands on its two legs, and has basically a horizontal body position. Out to the front, you've got the arms, the torso, and the great big head, puts a lot of weight on one end of the seesaw. And the idea is, well, if you don't have counterbalance on the other end, in the form of the big long tail, T-Rex is out of balance and it teeter-totters flat onto its face. So you have to have the big tail for that function. But if you think about the tails of dinosaurs, they most closely actually resemble big tails like we see in a lot of modern day reptiles like crocodiles and big lizards. And those are animals that are not at all built like seesaws. They walk around on four legs, and yet they still have very large tails. And the question is, really, what is their function? And I began my research on dinosaur tails by performing a bunch of dissections on a whole bunch of modern-day reptiles. So I cut through the skin and the scales. I peeled it back to have a look at the anatomy that was underneath. And it turns out a major function of the tail in modern-day reptiles is tied directly to locomotion. They have this great big muscle position at the base of the tail, right behind the hips. Long muscle, it's called the caudofemoralis. If you're good with your Latin roots, caudo refers to tail, and femoralis, of course, refers to the femur, the upper leg bone. It's because this muscle is attached by a tendon that runs directly to the femur. And when this muscle contracts, it will pull backwards on the leg. Or if you're using it when you're walking, you take a step forward if you're a lizard, you contract your caudofemoralis, and that pulls your body forward. You can take another step and repeat that process. It's the single largest hind limb retractor muscle in a croc or in most lizards. And as it turns out, most dinosaurs were the same way. Tyrannosaurus rex is a tail-propelled critter. So I tell people, when you're thinking about the function of T-Rex's tail, don't imagine a seesaw. Instead, think of it like a Volkswagen Beetle, because it's there in the trunk that you're generating all your locomotive oomph.
So this muscle, obviously humans don't have tails anymore. Do we still have this muscle?
No, we have lost it. So our mammalian ancestors lost this caudofemoralis a long time ago. And an interesting question is exactly why we did that, why our ancestors abandoned what had been the primary hind limb retractor, because you can find this, you do a dissection on a salamander as well. So it goes way far back into the origins of tetrapods. Why the mammal line lost it is really unknown. One possibility, one hypothesis that I've put out there into the literature is that it may have been lost because there was this evolutionary bottleneck coming out of the great in Permian mass extinction, biggest mass extinction life on Earth has ever gone through. The representatives of our ancient lineage that made it through that seem to have been burrowing critters. Indeed, hiding underground may have helped them to sort of wait out the extinction. They survived the apocalypse by taking shelter in their underground burrows. And burrowing animals today, you think about rabbits, think about moles, etc. They tend to have a reduced tail. That's partially because when you're in a burrow and you've got a great big long tail, it makes it that much harder for you to turn around and maneuver in the tight space. It also tends to make it, that much shorter a distance that a predator has to reach in to grab hold of your rear end and yank you out. Also, just the act of digging tends to favor muscles in your forelimbs. That's what you're leading your excavation with. That's what you're shoveling through to create your tunnels. And so maybe that combination of factors led to a reduction in this muscle. And then after the extinction, when these were the animals that rebounded and came back above ground, that muscle had already been lost. It had been, decoupled, de-emphasized, and you weren't going to get it back. Instead, we do things a little bit different as far as our limb mechanics go.
So how can you tell that dinosaurs had these big muscles to help propel locomotion in their tails when all you have is bones? That's
right. Well, fortunately, bones often do actually give us a lot of direct clues to muscles. So the function of our skeleton does a whole bunch of different things. It provides passive support, holding us up to resist gravity. It can store calcium and some other important nutrients for us. It provides protection, obviously, but a major function of our skeleton is to provide a scaffolding against which our muscles can pull and move us about with. It's sort of the framework of the puppet that is us. And because of that, you can often see directly on bones the attachment sites for the muscles. You can see what we can refer to as trochanters, so crests on the bones where the muscles insert. Now, when I did my dissections of the modern day reptiles, I found this already been described in the literature. This is not like a new discovery, but I could see very clearly and I could measure precisely the size of what we call the fourth trochanter on the femur. That's where the caudofemoralis attaches. And you can see that very distinctly. It's a very tall crest of bone on, say, an alligator. You look at the femur of Tyrannosaurus rex. It's got the same muscle attachment, a really, really big fourth trochanter. That tells you without question that the muscle was there. Doesn't necessarily give you a great idea for how large it was. For that, I moved on to the tail vertebrae themselves, so the tails skeleton. And there I could identify, again, based on the dissections, the point where the muscle would attach, and I created a digital reconstruction of a number of dinosaur skeletons and a number of modern-day reptile skeletons, and came up with a way then to digitally recreate the size based on the constraints of these muscle attachment sites to figure out how big the caudofemoralis of different dinosaurs were. And one surprising thing that came out of that was it turns out Tyrannosaurus rex does not have a caudofemoralis relative to its size that is as big as what we see see in a crocodile or a lizard. It's actually bigger. T-Rex has got a beefier tail. And really, that's not so terribly surprising. After all, Tyrannosaurus rex is an active, fully terrestrial critter. Surely it should be doing more moving about and have a greater investment in walking and running than would an alligator or a crocodile.
So what does the size of this muscle in the tail, how does that feed into information about how these dinosaurs would have moved about in their day-to-day life?
Sure. So you can do, once you have an idea of what the size is, you can do some attempts at estimating like the cross-sectional area of the muscle to give you a sense for how much force it could have generated, or at least to bracket that in some way to have a sense for how much of an investment you have in it. Another thing you can do is look at where the attachment site on the leg is, because that makes a big difference too. In Tyrannosaurus rex, the attachment site is very high up. It's very close to the hip. So it's close to the point where the leg swings back and forth, back and forth, back and forth. On a lot of plant-eating dinosaurs, for example, you look at a duck-billed dinosaur, the attachment site is down very, very low. And this is an arrangement that we often see in muscles of a lot of modern-day critters, this trade-off between a high versus a low attachment, because that makes a big difference as far as leverage and as far as the distance that muscle has to contract. So with the attachment up high, like in T-Rex, a very short contraction of the muscle can swing your leg all the way through one step. That's good for moving fast. But having it down low gives you a longer moment arm, gives you greater mechanical advantage. Now, you have to either take shorter steps or else much slower ones. But it gives you a little bit more of an advantage as far as things like endurance goes. It pays off for that. So that makes sense. Tyrannosaurus rex as a predator is geared a little bit more, we think, towards achieving a high maximum speed. You can think of that like a higher, overtake speed. I can run fast enough to catch what I need to catch. Whereas plant-eating dinosaurs, which are more in the slow and steady category, have got a better leverage arrangement.
So in your book, you actually spend probably a chapter going through all of the details of how we might know who would win in a foot race between a T-Rex and a duck-billed dinosaur. Right. I guess my question is with this, when we're putting together, when you're looking at the muscle attachment sites and the muscle sizes and estimating how efficient and what sort of endurance an animal might have had, what sort of error bars do you have on those sorts of numbers? Sure.
So there's a question here, are we safe to actually even think about trying to put a number on it? I try to shy off from putting a speed limit or a range of speeds on how fast T-Rex or a duck-billed dinosaur or any dinosaur could necessarily run, because the range of speeds is going to be actually quite large if you're honest about how certain you are in the numbers that you're getting. But you can, I think, do a pretty good job of making these one-to-one qualitative comparisons between the different dinosaurs when you're looking at like one particular aspect. Yes, we can say this is clearly the adaptation that gives you greater mechanical advantage. Yes, this is clearly having a longer leg. That definitely has implications for maximum running speed and things like that.
Once you go through and you figure out how big these muscles might have been in the tails, do those tails look anything like what we're used to seeing illustrated in books for dinosaurs?
Well, oddly enough, if you go back to some of the older dinosaur illustrations, things done by like the great paleoartist Charles Knight, that was back when paleontologists were using reptiles more for their models. They were basing their reconstructions on their anatomy, and some of those old school illustrations, although they got lots of other problems with them, their tails are closer to what we think is now the case. But there was a period of time when a lot of paleo artists were giving dinosaurs these super duper thin sort of rat tails. And that was in part because giving Tyrannosaurus rex a tail that is sort of sleek and laterally compressed, a skinny tail, makes it look, that much more dynamic. It looks like that's the tail you expect to have on a faster animal. And of course, there was a big revolution in our thinking about dinosaurs, recognizing that they were much more active animals than what had previously been thought back in the days of Charles Knight, etc. But as it turns out now, that was that was an error. That was something that needs to be corrected, because actually, if you want to make Tyrannosaurus rex fast, if you want to draw it with the ideal anatomy for moving more quickly, the answer is you don't reduce the girth. You don't subtract weight from the tail. You add it on, because that's where the running muscles are located.
With animals like the long neck type dinosaurs that
yes.
probably would have mostly been down on all fours, are their tails, I guess, on a, when you correct for the size difference between the two types of dinosaurs, are their tails less beefy than a T-Rex that was up on its hind legs?
They are, in fact. So most theropod dinosaurs, so the bipedal meat eaters, have got actually a special adaptation in their tail to increase the size of the caudofemoralis. They've made some anatomical modifications to accommodate a big muscle. And what they've done is they've raised up what we refer to as the lateral processes of the vertebrae, or the caudal ribs. So running down the spine on each vertebrae, there are these prongs that stick out to the side. They're major functions for muscle attachment. And in most animals, the position of these caudal ribs is fairly low down. But in theropod dinosaurs, they get raised up. They have an elevated position. And as they get raised up, that creates an expanded region below them. And that's the region that we know from modern-day critters the caudofemoralis muscle filled. So bipedal theropod dinosaurs definitely have an adaptation for extra beefiness in the back.
Is there any indication on the skeletons for other sorts of soft tissue that would have been present in the tail, like cartilage or fat deposits or anything like that?
So first off, the tail is often a region where fat is deposited. If you overfeed your pet tegu or your iguana, you can get a bunch of tails ballooning out of control. There's no direct evidence so far of large fat deposits in dinosaur tails, but there are plenty of other things like muscles and ligaments that you can look for clues for. Now, if we're talking again about some of those herbivorous dinosaurs like the duckbills, you actually don't, if you want to find things like tendons, you don't necessarily have to be looking for soft stuff, because an adaptation that those dinosaurs have is what we call ossified tendons. So those are tendons that have actually turned into bones. So they've got this sort of lattice work of these elongate tendons running down their backs and running down their tails. And the primary function of them, near as we can figure, is to aid in stabilizing the tail. So they help to hold it, and maybe they add a little bit of elastic extra springiness to the tail as well.
Okay. Is there, between the muscles and some of these dinosaurs that do have the ossified tendons,
yep,
do we have a good idea of how much movement dinosaur tails would have been capable of?
Sure. So that really varies depending on the dinosaur that we're talking about. Again, if we pick T-Rex as sort of a baseline, even across the tail of T-Rex, there is variability in flexibility. At the base of the tail, right past the hips, there's a region where there seems to be a lot of flexibility. But as you progress towards the tip of the tail, you get these elongate processes on the tail vertebrae that interlock with each other. They sort of fit together a little bit like Lego pieces. And the longer these prongs are, the more they abut against the next vertebrae in the series. And that creates a stiffer hold to them. If you're a fan of old dinosaur movies, which I am, and you watch the original King Kong, not the new one, but the original go motion one, when Kong fights the T-Rex, there's a great scene where the T-Rex kicks Kong off of him and then turns its back to the camera and it swishes its tail just like a snake. It looks really, really cool and dramatic. Could not happen. T-Rex could not do that. It could wag its tail at the base, but towards the tip of the tail, it could not swish it strongly side to side. Now, some other dinosaurs, if we want a tail that is super flexible, we can talk about, again, the sauropods, the long-necked dinosaurs, in particular the diplodocids, which have some of the longest tails of any critter ever. They have got adaptations towards their tail tip for extreme flexibility between the vertebrae. They've been sort of compared to having sort of a chain of nunchucks, just a lot of flexibility there at the end, and computer simulations that have been done by other researchers indicates that if you consider that flexibility and you also consider the amount of power the dinosaur has at its tail base, the thinking is that theoretically there's nothing stopping this dinosaur from swinging its tail so fast that the end of it would crack just like a bullwhip. It would actually create a sonic boom. Yeah.
One of the problems with fossils is figuring out whether what you've got is a juvenile or an adult, and if you're seeing any sort of sexual dimorphism, or if you just have a different species of dinosaur. Is there anything in tails that would help indicate sexual dimorphism in dinosaurs?
Sure. So funny enough, there may very well be. There's a group of dinosaurs that we call the oviraptorosaurs. And don't let the raptor part scare you, although they're fairly close relatives of the sickle claw guys like Velociraptor. This is a group of primarily vegetarian dinosaurs. In fact, they don't even have teeth. They've evolved a beak to replace it, and it's more of a cropping beak that you would like you would see in some tortoises. Anyway, oviraptorosaurs have been discovered in beautiful fossil deposits over in China, where you've got the fossilization of some soft parts of the feathers themselves. And a weird thing that they've got going on is on the very tip of their tail, they've got this fan of feathers. Now, oviraptorosaurs are not that close to the bird lineage. These are not flying animals. These are broad tail feather fans that have got nothing to do whatsoever with flight. But if you look today at a lot of modern day birds that do have feather fans, and a lot of ground birds, they employ them not to help them sail through the air, but as something to wiggle and something to wag during courtship displays. And so we've identified this group of dinosaurs that has got this tail investment in the act of showing off to the opposite sex. And we would predict, therefore, that this might be something that proves to be sexually dimorphic, because, of course, you think about the tail feather fan of a peacock versus a peahen. The males are the ones that usually do most of the displaying, and so we would expect that the male oviraptorosaurs would have a greater investment in tail flaunting, in tail dancing. And we have identified on a pair of specimens of the oviraptorosaur called Khan from Mongolia. A pair of specimens have been nicknamed Romeo and Juliet, because they seem to have met a somewhat romantic but tragic end. They were basically sort of cuddled up right next to each other, and it seems they got buried in a sandstorm or maybe a collapsing sand dune. Well, if you look at the tail bones of Juliet and you compare them to the tail bones of Romeo, and they're really different. Romeo has got much longer, much broader, what we call chevrons. Those are bones at the base of the tail. And that suggests that even though they're basically identical in every other piece of their anatomy, this big difference in the terms of the tail form suggests that, well, maybe Romeo's got broader chevrons to aid in the attachment of bigger tail muscles because it needs to do that much more dancing. And some recently reported findings from Mongolia by some of my colleagues at the University of Alberta have actually identified a similar development in some other Oviraptorosaur specimens. So it looks like this possible case of sexual dimorphism occurs in at least 2 different species. And as we get more and more data, more examples, more skeletons from representatives of the same species, I predict that number is going to grow.
Is figuring out whether something is sexual dimorphism or a juvenile or a different species just really a question of how many fossils of that species we have?
Yes, it is. In that, if you get enough skeletal specimens of that species, you're probably going to be able to arrive at the right conclusion. That's not all there is to it, though, because the fossil record is just so gosh darn sparse. We can't afford to always wait around, or at least we won't let ourselves wait around until we've accumulated enough specimens. So there's lots of work that goes into trying to figure out whether or not we ought to be lumping a whole bunch of dinosaur specimens into the same species, or whether or not we ought to be splitting them off into various different species. And some of the other tools that we can use to try to address that question, we can look at if we think maybe it's a change that's occurring as the dinosaur grows up, we can look at bone histology. That means we can slice into the dinosaur's bone, take a look at its internal structure, get an idea for how old the individual is, what growth stage it was at, and that will hopefully help us know if we're making the mistake of just splitting off a baby from its parent.
Okay. A few years ago, a feathered dinosaur tail was found preserved in amber.
Yes, absolutely.
Did that add new information to some of your research into this topic?
Sure. So first off, that was some of my research. So I was a co-author on that paper describing the amber specimen. That was definitely really, really cool. That told us some new stuff about dinosaur feathers themselves. It was tricky, though, to actually identify what particular kind of dinosaur the amber tail specimen came from. Now, we're pretty sure it's from a small theropod dinosaur. If you want to envision it, it's probably something fairly similar in body form to Velociraptor, although probably not in the raptor group proper. But I tell you, the coolest thing about that discovery was that it broke down what we thought were the barriers to dinosaur preservation. We had found previously, specimens from China where you had the impression and the stain of the feathers preserved flat, in a slab of stone. But with amber, you get not just a 2-dimensional view, but you get a 3-dimensional view, right? It's stuck in this gunk. You can twirl it around and you can look at the structures of the feathers, the structures of the bones, beautifully preserved in 3D. And there's other stuff there too, not just feathers and bones, but some other soft tissue that's dried up next to it. We got what we think is actually a residue from the dinosaur's hemoglobin. So some iron that indicates dinosaur blood preserved in amber. That's something we thought was just in science fiction a couple years ago. And so what I think is really cool about this is it indicates, we're going to be finding more of these specimens as we continue to work these amber deposits in Myanmar. And I would say, stay tuned to that, because that is really a matter of time before we get, more than just the tail end of a dinosaur. We're going to start getting, for small dinosaurs, other bits and pieces. And they've already pulled out some beautiful, true bird specimens from those localities as well.
When you mention evidence of hemoglobin preserved in amber, we're not talking about actual intact hemoglobin, are we? It's
no,
just...
absolutely not. We are definitely not going to be able to clone a dinosaur from these amber specimens.
That was my follow-up question, obviously. Yeah. So when you're investigating a fossil that's preserved in amber, does the fossil get, I guess, excavated like you would with a fossil that's in a rock, where you chip away do you chip away all of the amber around the fossil, or do you leave it in the amber and work with what you can see?
No, you don't. So for the most part, you leave it in the amber and work with what you've got. There may be cases where if you really need to get a sample or something like that, or you need, again, to do some histology work on it for whatever reason, you may choose to slice it open. Fortunately, though, amber is largely transparent, or at least translucent. So you can usually see what you need to see without digging in and removing it. And indeed, you normally don't want to remove the amber because it's doing the job of preserving the thing for you. It's holding it together.
Were you able to see other soft tissues underneath the feathers, like the muscles or the skin for the tail?
Sure. Yeah, absolutely. So you could definitely see where some things were, they're dry, they become dehydrated. Right. But you can definitely make them out. And for that work was also done trying to get the specimen essentially X-rayed, and we were able to create a digital model of the bones inside the amber.
Okay. So changing topics a little bit, you've also worked on displays for a few different museums and curated exhibits for the museum at the University of Alberta.
Yes.
What actually goes into curating a museum exhibit?
Okay. Well, that depends on, how far down in the process you want to start. A lot of people think that, you dig up a dinosaur and that's it. It's ready to go on display in the museum. That's obviously not the way it goes. You dig up a dinosaur, then you send it back to your museum, and then you usually spend, up to like 10 times, the amount of labor that was put into excavating the fossil in the field, into cleaning the fossil up in the laboratory, because they don't come out of the ground usually looking pretty. Usually they still got a lot of rock encoding them. The bones, once you expose them to the air, once you remove the rock that's been holding them in position, they tend to be very, very crumbly. So you've got to glue them together. Mm-hmm. But once all that's done and you're ready to put a specimen out onto display, then you've got to think about, what story do you want your exhibit to tell? I don't like it when museums just present dinosaurs as sort of a parade of monsters. Here's a specimen, it's this dinosaur. Here's another specimen, that's from that dinosaur, so on and so forth. So when I did, for example, the Discovering Dinosaurs exhibit with the University of Alberta, we were very mindful of trying to tell, of using the fossils collectively to tell a greater story about the ecology of, in our case, prehistoric Alberta. So we began by sort of working our way up the prehistoric food web with the plant fossils, with the smaller reptiles that inhabited the dinosaurs world, with the crocs, with the turtles, with the champsosaurs, and then we moved up to the different herbivorous dinosaur families, and then ending, of course, at the top with the tyrannosaurs.
Have you ever made a display and then a new publication came out that made you realize you had it wrong?
Let me think. Well, I'll tell you one new thing that's come out recently that I was a part of was the discovery of skin fossils from Tyrannosaurus rex. Now, again, we've known from specimens from China that many dinosaurs have got feathers, and among them were some of the early tyrannosauroids. So early tyrannosaurs have got this fuzzy hair-like covering of feathers holding in for insulation. And because we found it in those guys, we assume, well, that continues all the way up the family tree. And Tyrannosaurus rex was probably a fuzzy dinosaur. Well, then we got these skin fossils, and they showed us that at least in many patches across the body of Tyrannosaurus rex, there were scales, with no strong evidence for feathers. Now, that's not to say T-Rex did not probably have some feathers. It probably did have some, and it certainly may well have had a whole bunch when it was young and growing up. But when T-Rex got to be really big, it seems like a lot of its fuzz was lost. And that may be for the same reason that today a lot of big mammals that live in warm environments, like elephants and rhinos and hippos and Cape buffalo, tend to have fairly very sparse hair, because when you get to be so large, your body heat is held in by virtue of your great bulk, and you're actually more concerned with losing heat than you are retaining it. Another big example of a similar phenomenon happened to me when we were doing the online courses, because I just finished writing a section about Scansoriopterygians. These are small dinosaurs. They're super duper tiny. They're known from Asia. They're these tree climbing things, and some of them have got this one really, really super long finger. And the thinking was that these were dinosaur ii. So an ii is a lemur in Madagascar that has got a really long finger, and it uses it as an insect probe, right? It'll bite a hole in the trunk of a tree to get at tunnels that are made by beetles, and then it'll stick its finger into these beetle tunnels, skewer them on the end of its claw, and then pull them out and gulp them down. And the thinking was, well, this little dinosaur with a long finger, it's doing the same thing. That's pretty clever. Turns out, no, we were wrong in a spectacular way there, because then other specimens from China with soft tissue came out, and they show that, in fact, this was more of a dinosaur flying squirrel, that supported by this one elongate finger was this flap of skin, and so it was actually probably using it to glide, to hang glide through the prehistoric forest. And so I had to go back and rewrite what I'd written. In the end, that turned out to be a pretty good sort of demonstration of how science progresses.
Well, and I mean, when I was younger and, in my dinosaur kick, feathers weren't even in any of the books. And now
Absolutely.
we've got, like, your book has I think all of the living dinosaurs on the front cover of your book anyways have some feathers of some kind. Mm-hmm. And you've got predators in the book with fuzzy crests and all that sort of stuff. So it keeps changing. It's great.
Absolutely, absolutely. And one thing I'll add, too, is our understanding of the evolutionary history of dinosaur feathers is really changing rapidly right now. So what I've said about early feathers being fairly simple, fairly hair-like, and used for insulation, and then, of course, ultimately you get to feathers that are useful for forming airfoils and helping you to fly in birds, there's a big gap between those two forms. And to get more complex feathers that have this flat surface to them that are useful for flying, it seems now like maybe there was this intermediate stage of dinosaurs doing what those oviraptorosaurs were doing, developing more complex feathers with a flat, planar form, because that just helped you to use them for display. The old story of dinosaurs evolving flight, at least one version of it, was that, okay, you had a dinosaur that was gliding from tree to tree, and its feathers got more and more complex to help it do that. Well, now we have this other possibility, and what's going on is you have this intermediate sexual display stage that may turn out to be very, very important.
Okay. Yeah, I guess it wouldn't have occurred to me that would be the intermediate stage as a display.
No, but you can see how it's a great jump to go from fuzz to a wing. And indeed, whenever other animal groups have done that, right? When pterosaurs, the group that includes Pterodactylus and Pteranodon, when bats have done it, when flying squirrels have done it, even when Scansoriopterygians did it, they didn't develop some weird filamentous feathery thing to help them glide. They did it a simpler way, which is just to stretch some skin between your arm and your body. Yeah.
Yeah. Okay, that's fair. Yeah, skin, I guess, would be a simpler thing than a fully fledged flight feather.
You would think so. Certainly it has evolved more often.
Once we get a better idea of what sort of feathers various species of dinosaurs might have had, I mean, I have to imagine that'll change how they get illustrated quite a lot, because a bird with feathers looks a lot different than a bird without feathers.
Absolutely, yeah.
So you mentioned the online courses that the U of A has put together. Are the types of methods that paleontologists are using for outreach changing quite a lot these days? I imagine it probably used to be a lot of museums and TV, and now we have open online courses that we wouldn't have had 10 years ago. And we've got podcasts.
Sure. So I would say that I wouldn't necessarily say that things are changing, in that museums are still very much so the core of what we do. Paleontology is a specimen-based science. And I don't think there's ever going to be a real substitute for standing underneath a Tyrannosaurus Rex skeleton or Brontosaurus skeleton, staring up and marveling at it. But it is certainly the case that many, many new tools and evolving technology have added to what we're able to do, as it's added to what we're able to do in our research.
How do you decide for something like the open online courses what the target audience is?
Well, that's the great thing about dinosaurs. You don't have to decide what your target audience is, because your target audience is everyone. I think, everyone is interested in learning about dinosaurs. Paleontology is just a wonderful gateway science. It's a fantastic way of getting people, kids, adults hooked on science and interested in learning about all kinds of different things, right? I mean, you and I have talked about some basic evolutionary processes here. We've talked about some basic biomechanics, etc. There's a whole bunch of stuff that can be taught and is taught through dinosaurs.
And so with your book that came out last year, it's targeted at a younger audience.
It is,
although
for sure.
I read through it and I enjoyed it and I learned a lot along the way.
Well, thank you. Good. Yeah, I would say the target audience for that book was a younger version of myself. So I wrote the book with the idea in mind, what would I have liked to have been told when I was in elementary school that I wasn't being told in some of my dinosaur books.
Is there a topic that you would have liked to include in the book but just didn't have time or space for?
Oh, gosh, absolutely. There's so many topics. The book does have a fairly narrow focus in that it's about dinosaurs of the Alberta Badlands. So
Right.
it is, and Alberta is, I don't mean to say that is strictly a topic of local interest, because Alberta is one of the best places in the entire world to dig up dinosaurs. We know more about the dinosaur ecology in this thin section of Badlands than we do about it in anywhere else. It's our best window into the age of dinosaurs. But having said that, there are so many other dinosaur groups, so many other cool dinosaur discoveries that have been made all over the world. And obviously, those are not incorporated into the book.
Yeah, that's fair. I guess it is just about the Badlands. We're sort of spoiled in Alberta that we have the Tyrrell, which is such a great museum.
Absolutely. Yeah.
And it's not that far from most places in the province to get to a paleontology museum.
Sure, and it's not that far to get to a paleontological dig. So I'm in Edmonton, and we've got dinosaurs within the city limits. One of the first fossil localities I talk about in the book is the Edmonton Bone Bed. It's huge dino graveyard where a massive herd of duckbill dinosaurs, Edmontosaurus, as it happens, got wiped out and are buried there. And so for our at the University of Alberta, for our summer field schools, we take our students on a short drive to the spot in the river valley, and we can dig up dinosaurs within the city.
Yeah, that's one of those sites that I know it exists, but everybody's very tight-lipped about where it's located.
That's true. That's true. And to be honest, most of the time, there's really nothing to see there. So we cover up the site when we're done because we don't want erosion getting to the bones over winter, etc. So for most of the time, it's just this big patch of dirt.
Okay. Actually, a few years back in Edmonton, so a city crew found a dinosaur fossil while working on a sewer project.
Yes.
How does a dig site like that differ from one that's in an open area near the surface?
Okay. Well, I mean, dig sites come in a huge variety. But yeah, so here in Alberta, the reasons why we've got so many wonderful dinosaur sites like Dinosaur Provincial Park is because we are the lucky recipients of a huge series of geologic coincidences. So in order to get dinosaur fossils preserved, you've got to have dinosaurs dying in a place where their bones can be buried. So I'm not originally from Edmonton. I'm actually originally from the mountains of North Carolina. Technically, I'm a hillbilly. But back home is a terrible place to find dinosaurs. It made me very sad as a child. And that's because of the mountains themselves. Those Appalachian Mountains are very, very old. And they date back basically to when dinosaurs first evolved. And because of that, it means there were mountains when dinosaurs were there. Mm-hmm. Always have been. And because of that, if you're a dinosaur and you die in a mountain, even though you're there, gravity only works one way. Your skeleton and the sediments erode and they go downhill. Well, a great place to find fossils, a great place to be preserved as a dinosaur was in Cretaceous Alberta when we had beachfront property. Because global temperatures were high. And we were on the coast, and as the Rocky Mountains were being formed on the west, they would erode, and a bunch of sediment would fill in these coastal lowlands. So dinosaurs would die, their bones would sink down into the soft sand and the mud, and they would get preserved. And then as time went on and dinosaurs went extinct, more and more sediments piled up on top of the dinosaur-bearing layers. And that's the thing, right? In Edmonton, we strike dinosaurs sometimes when excavation crews are at work and they just happen to dig down low enough to get into this fossil zone. But in Dinosaur Provincial Park, what happened was that, just a few thousand years ago when the Ice Age happened and big glaciers swept down across North America, they scraped up a bunch of the upper layers of sediments. And then in the Dinosaur Park region, they melted, they pooled, and they did a whole bunch of erosion, digging down and exposing fully the dinosaur age rocks. And so that's where you can find them.
So another area in Alberta where fossils sometimes get dug up is up in the oil sands mines.
Yes.
Are mines in general a good place or a common source of fossils worldwide?
Sure, because they're an excavation, because they're digging down and getting into ancient rocks. So the worst places to have digs are where you've got a whole bunch of plants, a whole bunch of vegetation holding on to the topsoil and preventing erosion from happening. Of course, when you're mining, you are the erosion. You're digging through, and you're just moving through rock.
Okay. And the fossils that we find in the oil sands aren't necessarily dinosaurs. They're more marine life. That
is usually the case, for sure. And that's because that's where you're digging. You're going through these, dark, oceanic, shales, etc. But there are exceptions to that. So we are, often lucky enough to encounter an example of what we call bloat and float. So that refers to a common phenomenon of when a big animal will die inland, and as it starts to rot, it builds up with gases, and that makes it essentially a great big raft, a great big inflatable raft. And when there's a big flood event, or if the animal's dying in a wet environment, its carcass will float. It doesn't take very deep moving water to actually transport that specimen along, and it can take it out to sea. And then at some point, the carcass ruptures, there's that all the terrible noxious gas comes out, and the animal starts sinking down. And then you can get wonderful specimens preserved, because when you're buried on the seafloor in very, very fine sediments, you can get a lot of detail, and you're not going to necessarily be as disturbed as a skeleton might be on dry land, where a tyrannosaur or other scavenger could come along and start ripping it apart. And the great example of that is the wonderful Ankylosaur borealipelta that's on display right now at the Tyrrell. There we've got every single piece of armor across the front of this big armored dinosaur preserved, and it's just spectacular. You can see not just the big spiky pieces, but you can also see the little ones around them. It's a wonderful specimen that really makes the point that ankylosaurs should not be thought of as dinosaur tanks. They should not be thought of as dinosaur turtles. They're more like dinosaur hedgehogs. Their armor is not just super duper thick, it's really, really sharp. A T-Rex could easily crunch. It's got enough force to bite straight through the armor of most ankylosaurs, but it wouldn't want to do that because it would wind up impaling itself, lacerating itself in the process.
With fossils that are found on construction sites, is it, to a certain extent, is it just a matter of luck, whether the person doing the digging is observant enough to notice that they found something?
Usually that is the case. Now, of course, if you're doing a big construction project here in Alberta, you got to have some consultants, some people who come on site who look to see and verify that you are not going through something of important value to the province at large.
Oh, okay. Is there much of a problem with poaching or vandalism at dig sites? Because a lot of them are out in the open.
Oh, absolutely. So when I went to Mongolia, to the Gobi Desert, great place to find dinosaur skeletons. It's the only place I've ever been to where a dig really looks like it does in some of the opening scenes of Jurassic Park. You've got this great bit where they're just scraping away the sand, and there's this wonderful articulated, I guess it's supposed to be a velociraptor skeleton. And it's not the way you find dinosaurs, not what some of our dig sites here look like. In the Gobi, there are spots that really do look like that. Unfortunately, there are also places that just are these dinosaur craters, these spots where poachers have come in and they've just wrecked the skeleton. And they've done that because what they're going for are the teeth and the claws of the skeleton. They don't care about anything else. They just want these prize pieces because those are things that are of value on the black market and are small enough that you can smuggle them out. So a lot of beautiful specimens have really been destroyed in that way by sort of fossil poachers, fossil headhunters.
Is there much that can be done to prevent that sort of
There
poaching?
is. So there not a lot that can be done to prevent it directly. Huge badlands, huge regions like the Gobi Desert, you're not going to be able to police that. But what you can do, and what people all over the world can do, is crack down on the selling of these illegal specimens, because that is ultimately what is driving the system.
Okay. Do you have a recent discovery or a recent paper even that is your favorite?
So I'm often asked the variation on that question, which is, what is your favorite dinosaur? And I always like to say it's the one that I'm working on right now. And today, that makes my favorite dinosaur a specimen that we call Hannah. So Hannah is a ceratopsian, a horned dinosaur that I found a couple summers ago in the area around Dinosaur Provincial Park, and Hannah is like an animal we call Styracosaurus, or I would argue the most handsome of the ceratopsians, of the horned dinosaurs. Styracosaurus, envision Triceratops in your mind, take away the big horns over the eyes, but give it a much taller rhino-like horn on the end of its snout. And then on the frill, the big shield there at the back of the skull, you can add on a whole bunch of really long spikes sticking backwards. Styracosaurus has got this crazy punk rocker look to it. It's like something you would encounter late at night in the streets in London. And we've got this great skull of Hannah. By the way, because I found the specimen, I got to give it the nickname of Hannah. And so it's named after my dog. And Hannah is a dinosaur that we're working on. Right now, we've just finished doing some very cool laser scanning to give us a 3D reconstruction of the head. And we hope to have a paper on Hannah coming out pretty soon. Also, I've got a paper that's just been accepted on the huge Tyrannosaurus Rex, nicknamed Scotty. No relation to myself, but Scotty's from Saskatchewan, and that's a really cool T-Rex because it shows us, number one, a whole bunch of injuries. Scotty had a very, very hard life. It's got busted rib, maybe some evidence of a diseased jaw. It's got this impacted tooth. It was hard to be a Tyrannosaurus Rex. Kids always like to pretend to be T-Rex. I tell them, don't do that. It's not good to be a T-Rex. You got to make a living by attacking Ankylosaurs and Triceratopses. You're beaten up and you're dying fairly young. Scotty's also cool because it shows us really well preserved horns on the face of T-Rex. We don't normally think of Tyrannosaurs as being dinosaurs that have horns, but they do have little ones. The cheek of a Tyrannosaurus Rex has got this little jugal. In fact, if you look at the cover of my book there, the Tyrannosaur that's on, if you look just to the left of its nostril, there's this spike that's sticking out to the side, and it ends in a little stud, a little horn. You can also see there are these big ridges, these horn crests directly above the eye.
You mentioned there was evidence of a diseased jaw. Is there often evidence of diseases in fossils, or is that a pretty unusual find?
No, very often you will find some sort of evidence of disease or infection if you've got a big dinosaur skeleton. Many dinosaurs lived violent lives. I had a paper come out not too long ago about sauropod, a long-necked dinosaur that has this broken tail and a whole bunch of vertebrae seem to have fused together. This is a dinosaur that's got an aching tail to it. There's been some evidence even of identifying some bone cancer in duck-billed dinosaurs. One of maybe the most famous dinosaur injury is specimen of Allosaurus, big Jurassic carnivore that looks to have on its hips a big skewer mark where it looks like it got stabbed possibly by the tail spike of a stegosaur. A stegosaur caught it right in the rump. And coming off of this big spike impact wound, there's this hollow space that's got some gnarly bone around it. Looks like the stegosaurus skewered this allosaur. Allosaur did not immediately die. It probably limped away, and then the wound got infected. And this was a site where the infection was spreading.
Okay. So you can see that sort of thing, like a wound, an infection, and whether or not the dinosaur lived afterwards in the fossils themselves.
Yes. Oh, and another very cool example of that are specimens have been found of hadrosaurs, of duck-billed dinosaurs, that have actually got in their tail vertebrae Tyrannosaurus rex teeth embedded in them, and the tail has healed around them. Those are cool specimens because they have finally ended once and for all the debate, which was always pretty ridiculous, over whether or not Tyrannosaurus rex was strictly a hunter or strictly a scavenger. This could not have been a dead duckbill that the T-Rex bit into because it healed up afterwards. That debate is done.
I think I may have missed that debate. There was debate about that T-Rexes were just scavengers?
Yeah, absolutely, yep.
Huh. All right. Well, I mean, I assume they would scavenge if something was around, because...
Absolutely. Today, there are very few predators that do not also scavenge when the opportunity is presented to them. I have no doubt Tyrannosaurus rex was the same. I also have no doubt that when Tyrannosaurus rex was hungry enough, it was more than capable of going out and trying to procure itself a live meal.
Thanks very much.
Absolutely. My pleasure. Thanks for having me.
You can learn more about Dr. Persons and find links to his website and social media on our website, scienceforthepeople.ca. There you can also find past episodes, our social media links, and learn how to support the show. Thanks for listening, and we hope you'll join us next time on Science for the People.
Science for the People is produced by Rochelle Saunders and edited by Ryan Bromsgrove. Helen Quivalon is our publishing liaison. We get research help from Josh Witten and consulting support from Desiree Schell. Our frequently seen guest hosts are Marion Kilgour, Anika Hazra, and Jessica Yaros. Our theme song is called Binary Consequence, and it was written and recorded by Fractal Pattern. Science for the People is entirely listener-supported. You can find us on Patreon, where you can support us with monthly donations in any amount, or you can send us a one-time donation in any amount via the donate page of our website. Science for the People is created in partnership with the Skepchick Network, a collection of blogs, podcasts, and video content focusing on the intersection of science, popular culture, politics, and social justice. You can find out more about Skepchick at skepchick.org. The show is hosted by science news writer Bethany Brookshire and me, Rochelle Saunders.